talk about some properties, which is going to prevent us from having to do the limit definition every single time, which is going to be very helpful. So the first one, these are just some basic differentiation rules. The first one is the constant rule. So if I take the derivative, which this d over dx is another way we represent the derivative. So the derivative of c, which c in math is usually used to represent a constant, which means just a number, no variable with it. So the derivative of a constant is just 0. Why does that make sense? If I graph any constant number, that will be what type of line? Yeah, horizontal. So if I think about the derivative of that, like I talked about yesterday, if it's a horizontal line, the derivative is going to be 0. The slope of the tangent line is going to be 0. Okay, so it kind of makes sense if you think about it. Next rule is the power rule. This is the one that's very, very handy. The derivative of x to any power, so x to the 5th, x to the 4th, whatever, x to any power, is just n x to the n minus 1. Which basically, let's summarize what it is. The power rule basically says I do what with my exponent? So if n is my exponent, to take the derivative, I do what with it? Yeah, my exponent is n, so I bring my exponent out front. So I bring the n value comes out front, so I bring the exponent out front, and then I do what with the exponent? Subtract 1, that's it. So this is a shortcut. So the power rule says that I can take my exponent, move it out front, and then subtract the exponent by 1, and that's the derivative. So I look at a couple examples. Example 2, y equals 12. Okay, if I want the derivative, so dy over dx, which is another way we represent the derivative. The derivative of 12, it's just a constant, so it is 0. If I look at b, I notice that this is the 5th root. Now we always want to try to get it in exponential form, so we always want to try to write it as an exponent because I can use the power rule. So how can I rewrite the 5th root of x to be written as an exponent? Close. You're kind of the right idea. It's going to be x to the 1/5. So any root is always becomes the denominator. So that becomes x to the 1/5. Now we can use the power rule. So we want to try to get it in exponential form, so I can use the power rule. So now if I take the derivative, this is another way you might see it represented. If I have it in function notation, we usually use that little hash mark. So that means the first derivative. So the first derivative of f of x, power rule. Exponent comes out front. So 1/5, x to the, take your exponent and subtract 1. So 1/5 minus 1, or 1/5 minus 5 over 5 is negative 4/5. And I don't like negative exponents, so what can I do to get rid of the negative exponent? Yeah, move it to the bottom. So if I have a negative exponent, just move it to the bottom or to the top, whichever where it's starting at, and then just make it positive. And then finally, if I look at c, I have 3 over x to the 7th. Okay, before I worry about the derivative, we have to bring the 7 up top, so we can use the product rule or the power rule. So rewrite it as 3x to the negative 7th, and now we can go ahead and use the power rule. So as I look at the first derivative, y prime, we take my exponent and move it out front. If there's already a number out there, common sense would say we just do what with them? Multiply them. So bring your negative 7 out front. 3 times negative 7, negative 21. Subtract 1, so be careful if it's a negative exponent. Negative 7 minus 1, negative 8. So negative 21 x to the negative 8. I don't like negative exponents, so move that to the bottom. So negative 21 over x to the 8th. So like I said, this saves you a ton of time, because otherwise, if we did it like we did yesterday, I would have to go through and I would have had to plug in x plus delta x everywhere I saw x, get a common denominator, do all that crap. So this product rule saves you a lot of time. So you literally could go back through all we did yesterday and use this rule, and you would get the same answer for some of them. Some of them you might not be able to, but most of them you will be able to. Okay, sum and difference rules. All this says is if I take the derivative of two functions added or subtracted from each other. So if I take the derivative of two functions added or subtracted together, basically it's a polynomial. 2x plus 4x squared or something like that. So basically that's saying if I have if I'm taking the derivative of two things added together or subtracted together, if I had to use common sense, I'm thinking I could just do what? What would be the easy way? Like the straightforward way. If I took the derivative of two things added together, I can just take the derivative of each one separately. So this one is kind of makes sense. So I can just take the derivative of each one separately and then add them together. So this one's kind of straightforward in that aspect of if I have a polynomial, I can just take the derivative of each one individually and then just put them together. Now, not all of the rules are going to be straightforward. We'll get to a couple in the next couple days where they're going to be a little more complicated. But for today, they're pretty straightforward. Okay, any questions so far? Okay, example 7. I look at example 7, I want to find the derivative. First thing I notice is that this is a polynomial, so I'm feeling pretty good. Because if it's a polynomial, I can just take the derivative of each one separately and then put them together. That's what the sum and difference rule says. So first thing I'm going to do is I'm going to just rewrite this real quick. The first one. If I'm dividing by 2, how could I rewrite that as multiplication? Yep, negative 1/2 x to the 4th plus 3x cubed minus 2x. So I'm going to go ahead and write this one, the dividing by 2 as multiplying by a half. So when I do the power rule, I see what to multiply the 4 by. So it's easier to kind of see that. So now if I take the derivative, I can just take the derivative of each one separately, and that will be my answer. So if I look at the first one, I notice this is an exponential because it's x to the 4th. So I'm going to take my 4, multiply it out front, which will give me a what? Negative 2. Negative a half times 4 is negative 2. And then take your exponent and subtract 1. So that's going to be negative 2x to the third. The next one, 3x cubed, will be 9x squared. So 3 times 3 is 9. Subtract 1 from the exponent, 9x squared. And then negative 2x, if I take the derivative, my exponent is a 1 here. So that will be negative 2. 1 times negative 2. Subtract 1 from the exponent will give me x to the 0, which is just not there anymore. So that is my answer. So literally, if you did this with the limit definition, you'd have to take x plus delta x to the 4th, which would be a ton of work, but you would eventually get the same answer. Okay? Any questions on that? Okay, let's look at B. So I'm just kind of throwing in some different examples. I look at B and I notice that it's not necessarily written in polynomial form. So I can't necessarily just take the derivative of each one. But as I look at B, is there something that you notice I can do which will basically turn this into a polynomial? You're fine. What did you say? Say that again.
Like separate them,
Yeah, so separate them. You did this sum in Algebra 1, I think. 3x squared divided by x minus x over x plus 1 over x. So if I'm dividing by a monomial, which means that I have a single term in the denominator, you can take each term on top and just separate it out like this. So now if I simplify each one, I'm going to have y equals 3x squared over x, 3x to the first, you subtract your exponents, so 3x to the first, minus x over x, 1, and then plus 1 over x. Now I'm not going to, like the one example we did right above this, I don't like having, in order to use the power rule, I have to write this with an exponent. So plus 1 over x is going to be plus x to the negative first. So go ahead and rewrite that with the exponent up top, just so when I use the power rule, it's easier to kind of think about. So now I notice I have a polynomial, so now I can use the power rule. So y prime equals, if I take the first derivative of 3x, 3. 1 times 3 is 3. Reduce the exponent by 1, which will just give you x to the 0, so that's gone. Derivative of negative 1, 0. The derivative of any constant is 0, so that's gone. The derivative of x to the negative first, negative 1 x to the, reduce your exponent by 1, negative second. And I don't like negative exponents in my final answer, so that's just going to be 3 minus 1 over x squared. Okay. Any questions so far? The constant multiple rule I'm not going to go over because we already did. If you have a constant in front, you just multiply it by the exponent you bring out front. We already did it. I'm not going to worry about that. Okay, derivatives of sine and cosine function. The derivative of sine is cosine. So these are just kind of things you're going to have these memorized. The 6 basic trig functions. The derivative of the 6 basic trig functions memorized. So the derivative of sine x is just cosine. The derivative of cosine is negative sine. So there's the difference with that. So the derivative of sine is cosine. The derivative of cosine is negative sine. Okay. So basically, it doesn't really throw anything into it. You do the derivative the same sort of way, except you just know what these are. So let's look at example 8. We're looking at finding the derivative of some trig functions, sine and cosine. So if I look at this derivative, first of all, I notice that I don't have any exponents. So I'm not worrying about the power rule or anything like that, because these are trig functions. This isn't a polynomial. So I don't have to worry too much about the power rule. So as I look at this, if I want to find the first derivative, all we do is we say, okay, I have pi over 2 sine theta. Now pi over 2 is just a constant, because even though there's a pi there, that's still just a constant. So I just leave it out front. So pi over 2, what is the derivative of sine theta? So it's just pi over 2 cosine theta. So a constant out front just stays there, and then you just literally take the derivative of sine is cosine. Minus, what's the derivative of cosine theta? So I'm going to have minus negative sine theta, because the derivative of cosine is negative sine theta. And then the only thing to do to simplify is the minus minus becomes a plus. So pi over 2 cosine theta plus sine theta. Any questions on that? Okay, let's look at B. So I look at B and I kind of notice, okay, I kind of combined a trig function, a cosine part, and I combined an exponential part. So we're going to be using the product rule for the first term, and then the second one we're just going to use the trig function. So as I look at the first one, I'm not quite ready to take the derivative. I need to simplify a little bit. So what can I do to my first term to be able to simplify it? Yeah, so if I look at this, this is 5 over, let's simplify the bottom first. Let's actually cube 2x. So this will be 8x cubed. I have the plus 2 cosine x part. So we're going to actually cube 2x, so I'll get 8x cubed. And now, like I said earlier, I don't want to deal with the 8x. I have to put the exponent up front or on top so I can do the product or the power rule. Now be careful, the 8 has to stay on the bottom because I'm not raising the 8 to the third, it's just the x to the third. So I move it up to the top, make it a negative, because I want to deal with the power rule. Now that 5/8 I could necessarily write out front. Now this is kind of redundant, but that's okay, I'll do it. That 5/8 I could write out front like this, which might be helpful to kind of see when I do the power rule what I'm multiplying -3 by. So now let's go ahead and do the power rule. So I have, bring your exponent multiplied by the constant out front. So -3 times 5/8, -15/8, x to the -4th, plus derivative of 2 cosine theta. Yep, 2 stays there. The derivative of cosine is a negative sign, so -2 sine x. And then if I simplify this, we need to bring my x to the 4th in the denominator because I don't want to leave it with a negative exponent. And then it just becomes 2 minus 2 sine x. That's my answer. Okay. Any questions on that? Okay. So far, so good? Hopefully, maybe. Okay, let's go ahead and look at example 3. I'm actually going to look at part B. I'll go back to if I have time. But for part B, I want to find the slope of each graph at the given point. So if I think about this, I want to find the slope of the graph at the given point. So basically what I'm looking for is I'm looking for the slope of the tangent line. So what we talked about yesterday, the slope of the tangent line is literally a given point will give me the slope.
That's the definition of a derivative. So as I look at this one, at the f theta, I want to find the derivative of f theta at that specific point, 0, 0. So we're going to take the derivative of f theta. So f prime theta, because that is the derivative will be the slope. So 4 sine theta, what is the derivative of 4 sine theta? 4 cosine. The derivative of sine is cosine. The 4 just stays there. So that's 4 cosine theta minus theta. So what is the derivative of just theta? Think about this as just x. Don't get confused because it's theta and it looks fancy. If this is just x to the first, the derivative of just x would be 1. So the derivative of theta is just 1. So minus 1. Now I want to know the slope at 0, 0. So I'm going to take my function, my first derivative function, and I'm going to plug in theta. Now if I look at an ordered pair, which value, think about graphing trig functions, which value is theta? So if you think about graphing trig functions, which value is theta, is the angle? The x or the y? The x-axis or the y-axis? So when I graph like a sine, it goes 0, pi over 2, pi, 3 pi over 2, 2 pi. So what axis is my angle? X. So I look here, so 0, the x value is my theta. So I'm going to plug in theta. So to evaluate it, to find the actual slope, you plug in your x value, or whatever, it's f of theta, so I plug in theta value. So 4 cosine theta, which is 0, minus 1. Cosine 0, 1. So 4 times 1 minus 1 is 3. So the slope of the line at that point is 3. So find the derivative, plug in your x value or your theta value in this case. Do it. Here, because the derivative of theta is just 1. Because if I think the exponent is 1, bring it out, so negative 1, and then reduce theta by 1 would be theta to the 0, which is just gone. Any other questions? Okay, example 4. Find the equation of the tangent line to the graph of f at the given point. And it should be a given point at 1, 2. Sorry, I forgot to type it in there. So the given point is 1, 2. So at 1, 2. So let's think about this. I want to find the equation of the tangent line. We kind of did this some yesterday, but we used the formula. So if I want the equation of the tangent line, I'm thinking y equals mx plus b. So similar to what we did yesterday. What two things do I need to find? M and b, slope and y-intercept. The first thing I want to look for is slope. So once I find slope, I can plug in x, y, and slope to find b. So if I'm looking for the slope of this, it is the derivative. That is what slope is. The slope of the tangent line is the derivative at the given point. So we're going to go ahead and take the first derivative of this function. So if I look at for taking the first derivative, I notice it's not necessarily written with exponents yet. So is there something I can do to this function that I can do to get it in exponential form? So I can use the power rule. Yep. The fourth root of x to the third is the same as x to the 3/4 power. Your denominator becomes your root. Your numerator becomes your exponent. Now, like we did before, I have to get the exponent on top so I can use the product or the power rule. So this is going to be 2x to the negative 3/4. Okay, let's go ahead and take the first derivative. So f prime of x, okay, is power rule. So negative 3/4 times 2. Which reduces to negative 3/2. So negative 3/2. X to the, reduce your exponent by 1. Negative 7/4. Good. Any questions on that? Okay, now let's go ahead and rewrite this. So if I rewrite this, I'm going to have a negative 3/2. I have a negative exponent. So I'm going to rewrite x to the positive 7/4 on the bottom. But x to the positive 7/4 is the same as the I have a fraction as an exponent. So how do I rewrite it back in radical form? Fourth root of x to the 7th. So I move it to the bottom to make it a positive, and then instead of x to the 7/4, I write it as the fourth root of x to the 7th. So that is my formula for the slope, basically. So that is the first derivative, so that is the formula for the slope. But I want the slope at the given point. So I want the slope, I want the first derivative at 1, when x is 1. So I'm going to take my derivative and plug 1 in where x is. So negative 3/2, fourth root of 1 to the 7th. It's a 1, so that's not too hard. So what's my final answer going to be? Negative 3/2. So that is my slope. So if I want the equation, make sure you actually answer the question. I want the equation. So that's going to be y equals negative 3/2 x plus b, like we did yesterday. I need to find b, so plug in x and y. So y is 2, x is 1, so that's the negative 3/2 plus b. Add 3/2. Two plus 3/2. 7. Yep, 7/2. And then make sure you write your final answer. Y equals negative 3/2 x plus 7/2. Okay. So very similar to what we did yesterday, except it's a lot easier because you didn't have to use the limit process. You could just use the shortcuts we talked about. Okay, any questions? Okay, now we have some story problem, which is everyone's favorite. And we're going to have a whole lesson of story problems later in the chapter. So rate of change. So as I think about a rate of change, whenever I refer to a rate of change, I am talking about the derivative. Because if I think about what derivative means, derivative is the slope of the tangent line. So what two rates are changing? What two things are changing when I talk about derivative as the slope of the tangent line? We talked about some yesterday. Derivative is the slope of the tangent line. So what two things are changing in relation to one another if I think about the slope? X and y. So like I talked about yesterday, when I think about the derivative as the slope of the tangent line, that is the change in y over the change in x. So when I talk about derivative is just how two things are changing in relation to another. So slope was y over x. It always doesn't have to be y over x. Just in general, the derivative is the rate of change, or how two things change with respect to each other. So let's go ahead and look at the first example. Anybody who's taken physics, you've kind of seen these before. The position of a particle is given by the equation S equals f of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s is in meters. Now just FYI, anytime they give you S equals, S will usually be position. So as you're going through this, if they don't actually say this is the position function, if they use the variable S, that is usually position. Now as I look at this, these are referred to as PVA types of problems. Position, velocity, acceleration. So those words should kind of somewhat be familiar with you. So, any Physics 2? Anybody take Physics 2? I think you do this in Physics 2. I don't think Physics 1. I'd be surprised. Okay? You might. So as I go from position, velocity to acceleration, you take the first derivative every time you go from one. So if I give you the position to get to velocity, you take the first derivative. To get velocity to acceleration, you take the first derivative. So PVA, that's just the order that I take the first derivative. So the position to velocity, I take the first derivative. Velocity to acceleration, I take the first derivative. So if I give you the position function, part A wants to know the velocity at time t. So if I give you the position function, how do I find the velocity function? Take the first derivative. So to go position to velocity, I take the first derivative. So v of t, at time t, the velocity at time t, I take the first derivative of the position function, which is just going to be what? Yep, minus 12t plus 9. It is just a polynomial, so I can use the power rule. T cubed, 3 out front, reduce it by 1. 3t squared minus 12t plus 9. So that's my velocity formula. Velocity function. Part B, I want to know the velocity after 2 seconds and after 4 seconds. So if I think about it, how will I find, if there's my velocity formula, how will I find the velocity after 2 seconds? Plug in 2 for t. T represents time. So v of 2, the velocity after 2 seconds. I'm going to take 2, plug it in for t. Now, they're going to be picky about the labeling, so make sure you label it correctly. So let's use your calculator for this. You don't necessarily need your calculator, but that's okay. When I go through and do this, I'm going to get what? -3. Is that what we got? -3? Now velocity is measured in what? If it helps, velocity is very similar to speed. It's the same sort of labeling. So if speed would be miles per hour, in this case it would be meters per second. So meters per second. So velocity is always measured would be meters per second. Okay, the next one, I'm going to not worry about 4. 4, you would do the same thing, plug in 4 for t. The next one is I want to know when this particle is at rest, I believe. So if I want to know when this particle is at rest, if I am at rest, that means my velocity is what? 0. So I'm going to take my velocity and I'm going to set it at 0. So I'm literally saying when is this particle at rest, which means when is my velocity 0. Now think about what it's asking for. I want to know when, so I'm asking for a time. So when I want to know after how many seconds. So I'm looking for t, I'm looking for a time. And I want to know when it's at rest, so my velocity is 0. So as I go through this, it's quadratic, so if I want to solve this, I'm thinking factor out first. So I can factor out a what? 3. So I'm going to have t squared minus 4t plus 3. So it's a quadratic. I usually always try to factor first. How can I factor it further? Yeah, t minus 3, t minus 1. They multiply to give you positive 3 and add to give you 4, or negative 4. Now if I take each part and set it equal to 0, my two answers would be 1 and 3 seconds. Now why does it make sense by looking at my function that I might have 2 times when it is at rest? It's just square, so it's a quadratic, so my graph will look like a parabola. So if I think about the graph, it's a parabola, so it's going to have a starting time and an ending time. So I should have 2 positions, or 2 times when it is at rest. Okay. Any questions on that? Okay, next one, let's look at D. Question D, I want to know when is the particle moving forward? That is, when is it in the positive direction? So if we know anything about velocity, what is velocity when I am moving forward? Physics people? Velocity has to be positive. So if I think about moving forward or in the positive direction, my velocity has to be greater than 0. So I want to know what times am I moving in the positive direction. So let's think about this. B of t has to be greater than 0. Let's use the factored form of velocity. So 3t minus 3t minus 1. So I want to know when those are greater than 0. That will tell me when I move in a positive direction. So I move in a positive direction when t is greater than 3 seconds and when t is greater than 1 second. So same sort of idea, you're just setting it greater than 0 because I want to know when it's moving in a positive direction. So my velocity has to be positive. Okay, we're not going to worry about E real quick. We're going to skip E. Okay, let's worry about B. Let's worry about the next one. If a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is represented by this equation, this function. It is S equals. S always usually equals what? I tell you S equals, that's what type of the function? PVA. S is position. So whenever it's S equals, it's usually position. So this is the position formula. So I want to know what is the maximum height reached by the ball. So if I think about this, first of all, look at your function. It's quadratic. So what type of parabola is this? It's quadratic. I know it's a parabola. Just by looking at what else do I know about the parabola? Do what? It's going down because I see a negative in front of t squared, so I know it's going down. So something like that. Now, why does that make sense with the story problem? Yeah, I'm throwing the ball up. So if I'm throwing the ball up, it's going to go up and then come back down. So that kind of makes sense with what the function looks like. So if I want the maximum height reached by the ball, what part of the graph of the parabola do I actually want to know? The top, the vertex. So this would be the t value, and this would be your s, or your position. So if you look at your function, you can label your axes. T is inside it, so that is my x-axis, so time is my x-axis. S is my height, or my position. So as my time increases, the height is going to get big, it's going to get higher, and then it's going to get lower as it comes down. So if I want the maximum height reached by the ball, I basically want to know the vertex. So how do I find the vertex of a parabola? Remember the formula? The formula is x equals. In this case, it's going to be t equals. T equals negative b over 2a. That would give you the t value or the x value of your vertex. So hopefully this kind of looks familiar. Negative b. What is my b value? Yeah, that's fine. So if my b value is 80, so it's not necessarily first, the b is the number in front of the non-squared variable. So it's negative 80 over 2 times a. What is a? Negative 16. So if you plug this in your calculator, negative 80 divided by negative 32, 2.5 seconds. That is time. Does that answer the question? No. That gives you the time when it's at its highest point, but how do I figure out what the height is, what the position is? Plug it into S. So this is the time. I gave you the time. So this is the time when I am at the highest point. I want to know what position it's at. I want to know S if I give you time is 2.5. So you're going to take your original and you're going to plug 2.5 in because that represents the time. So I basically want to know what is the height when the time is 2.5. That will give me the highest point, or the S value of the vertex. If you plug that in your calculator, we are going to get 100. And that is position or height, so that will be 100 feet. Because it's 80 feet per second, so 100 feet. Okay? Any questions on that? Okay, part B. What is the velocity of the ball when it is 96 feet above the ground on its way up, on its way down? So 2 questions I want to know. What is the velocity of the ball when it is 96 feet above the ground on its way up or on its way down? First thoughts on this. What am I going to have to do first? I'm looking for the velocity, so I need the velocity formula. So that is the first derivative of the position formula. So my velocity formula will be 80 minus 32t. So I want to deal with velocity. That is the first derivative of the position function, which they give me because it's s equals. So there's my velocity formula. So if I think about what they're asking, I want the velocity when it is 96 feet above the ground on its way up. Let's think about this. Can I just plug 96 in where t is? No, because t represents time. Is 96 given to me in time? No, it's given to me in height. So what's the first thing I'm going to have to find? If I'm thinking to myself, I want to be able to plug time in to the velocity, what am I going to have to find first? So if I look, this is the velocity at a specific time. I don't know the time when it's 96 feet above the ground. So how do I find the time when it's 96 feet above the ground? What equal to 96? Huh? What will I set equal? If 96 is the height, what you're saying is put 96 for velocity. 96 is a velocity. So plug it in for the position one. So what I'm doing first is I want to find my time at 96 feet. I can't plug 96 in for t because 96 is a position, it's a height, it's not a time. So what I need to do first is I want to know what time, how many seconds is my height 96 feet. Because once I know that, then I can plug it into the velocity formula. If I look at this, trying to solve this, I would use what? It's quadratic, so I always try to do what first? Set it equal to 0. I'm going to move everything to the left. So it becomes a positive 16t. This should be a negative, sorry. Negative 80, because I moved it over. I made lots of... Okay. 16t squared minus 80t plus 96 equals 0. Sorry, I can botch that up. Okay, what can I factor out? 16. So if I take out a 16, that's t squared minus 5t plus 6. So it is factorable. If I factor it further, that's going to be 16 No, I don't think, is that, no, yeah, t minus 3, t minus 2. You want to say 6 and 1 because they're right next to each other, but it's actually negative 3 and negative 2. So if I set these equal to 0, the two times that my height is 96 feet is at what? Three seconds and 2 seconds. Now, like I said, it makes sense because I'm going up. So if I'm going up, I go up and then I go down. So I should hit 96 on the way up and on the way down. Now I want the velocity on the way up. So what is the velocity of the ball 96 feet on its way up? So if I want the velocity, this is my second part, I want to know the velocity when. On the way up, what will be the velocity at what time? 2 or 3? Think about it. If you think about it, if I want the way up, think about the graph. If I want the way up, am I going to pick 2 seconds or 3 seconds? 2. So I want the velocity at 2 seconds because that will happen first. So that'll be on the way up. So I take 2 and plug it into my velocity formula. So 80 minus 64, or 16. This is velocity, so that's going to be, how would I label that? Feet per second. Good. So that's the first question. That's the velocity on the way up. Velocity on the way down will be what? V of 3, because that will be the time when it's 96 on the way down. So 80 minus 32 times 3, negative 16 feet per second. Now, why do those velocities make sense? If I'm going up, it's positive, so it's a positive velocity. As I'm going down, it is a negative velocity. Okay, any questions on that? Okay, let's look at a couple more. Let's look at C. We can get through one more. I might be able to finish all of them today, which is fine. I can finish them tomorrow. Let's look at C. Sodium chlorate crystals are easy to grow in the shape of cubes by allowing a solution of water and sodium chlorate to evaporate slowly. If V is the volume of such a cube with side length x, Calculate dV dx when x equals 3 milliliters and explain this meaning. So as I look at this, I want to calculate dV dx. So like we talked about yesterday, dV dx is the derivative of v with respect to x. So what that means is I want to take the derivative of the volume with respect to x. So x has to be inside the function. That's what with respect to x means in terms of x. So as I look at this, I'm thinking, okay, I need to take the derivative, dv over dx, but I don't have a formula to start with. What formula from reading this can I come up with that then I can take the derivative of? Because I want to take the derivative of v, so I want a formula for v, for volume. Volume of a cube with side x. So what formula is the volume of a cube with the side length x? Volume of a cube. X cubed. Length times width times height. And if it's a cube, they're all the same, so it's x cubed. So the volume, which you have to kind of think about to get, is going to be x cubed. So if I want dv over dx, the derivative of that is going to be 3x squared. So this one's just a little different because you had to come up with the formula first. I want to know dv over dx when x is 3. So you just plug in 3 for x. Which is 27, label it, millimeters cubed, because it's volume. Now what does it mean? When it says explain its meaning, this is what my volume is approaching 27 millimeters cubed as my side length approach 3 millimeters. So as I look at it, the derivative is always how something is changing in relation to something else. So in this case, it's how my volume is changing. So it's getting close to 27 millimeters cubed as my length is approaching 3 milliliters. Okay? Let's do B. We can do B real quick. B doesn't take very long. Show the rate of change of the volume of a cube with respect to its edge length is equal to half the surface area of a cube. So volume of a cube with respect to a side length is going to be L cubed, like we just talked about. So volume is L cubed. That is the volume of a cube with respect to a side length. I want to show that the rate of change of the volume. Rate of change is always the derivative. So rate of change of the volume, dV over dL, is going to be what in this case? I want to show that the rate of change of the volume is equal to half the surface area of the cube. How do I represent the surface area of a cube? You take all the area of the sides and add them together. So how do I represent the area of one side of a cube? If I have a length L, side length L. L squared, how many sides do I have in a cube? 6. So my surface area is 6L cubed, and I want to show that's equal to half of that, which it is, 3L squared. Okay? Just kind of using derivative, stuff like that. So not necessarily hard, just kind of have to figure out what things mean. Okay, we're going to have to wait for the other two tomorrow, which is fine. Sorry, one of those days where you don't have much to look at. Okay, the homework, get out the